Hello, we're finishing up College Algebra 6.6. The recording cut out, but I'm sure you needed a break anyways. So we just finished up this kind of weird decimal number right here, and we were about to start this one that was almost the same, and we said it's probably going to be that reciprocal. So let's try it out. Oh, my pen's not going to work. All right, working pen. Okay, and so we said it's probably going to be the reciprocal because this one has those same numbers, but when I use my log splitter, this one would have the 9 on top. Remember to close that parenthesis, 2 logs, and you're going to get a crazy decimal. So you type it in, log of 9, close parenthesis, divided by log of 2. If you do have your latest, greatest calculator, you are welcome to use that special button. And remember to round it to 4 decimal places, which would make this 3.1699. Now just for funsies, type in 1 divided by and do that number, so second answer. And there's the last one we just got, 3155. It all goes together. Okay, now let's try it. That's one step trickier. So that same idea where it's a weird decimal number, but then there's a step after that. Okay, these are fun. Don't worry, we're going to use it all in the calculator. We just have to kind of line our thoughts out here on the paper. So first thing, I'm going to switch it to that log form. This would be log base 10 of 9 equals the exponent. Just this time our exponent is a little more complicated like these last few. This is going to give us a crazy decimal number. So log base 10 of 9. Well, if it's log base 10, I could actually just use my log button. Log 9. Okay, so punch that and you're going to get a crazy decimal. Log of 9. 0.95424, blah, 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 just like that. Keep it in your calculator. So I'm going to write this down just so you can kind of see you're on the same track as me. Dot, dot, dot. Now, to solve this for x, I next would need to subtract 1. So on my calculator screen with that number still there, I'm going to hit on the side the minus key, not the little negative, the minus key, minus 1, just like that. Should pop up and say ANS minus 1. Enter, and you should get this crazy little negative decimal, negative 0.04, dot, dot, dot. That's equal to the 2x. So the last step, I would divide it by 2. So with that still on my calculator, I haven't changed anything. I divide by 2 and hit enter. Should look just like that, ANS over 2, and give you this crazy decimal right here. So I didn't actually have a number until the final step, negative 0.022, rounded up, 9, 4 places. Okay, right there, 0.229. Let's try it again. I know that one's tricky. Okay, so same story. I'm going to first switch it to the log form. That would be log base 3 of 2 equals all this stuff, 4x plus 1. Okay, get this in your calculator. Use your log splitter if you have to. Log of 2 divided by log of 3. Make sure you're using that parenthesis. And what do you get? Log of 2, sorry, I hit the wrong button, 3. Okay, and you should get the decimal, 0.6309, dot, dot, dot. With that number, that crazy decimal on my screen, I would minus the 1. So remember to use the minus on the side. That's going to give me negative 0.369, dot, 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 dot. And then the last step, I would take that number and divide it by 4. So with that still on the screen, divide by 4, enter. For my final crazy decimal answer of negative 0.0923. 3, rounded at 4 places. Okay, kind of fun, right? It's all in the calculator. So there's not any hard math. It was just solving a linear equation. The trickiest part was just getting it into this log form. So remember, the base is the little base. The exponent is what it's equal to. The logarithm equals the exponent. And if you can get that, you've got it. All right, just a couple of word problems. Now remember, when we started this section out, we said the main place in real life we see exponents are in banking stuff. So we're going to switch back to that banking stuff. and see in that same kind of problem like we did way back in the first section 200 years ago, right? What if it was the time that we didn't know? What if the exponent was the mystery? All right, so same equation right here. They give us 3,900 that they want to put in as the principal. Okay. Hang on, let me switch it to my smaller pen so I have plenty of room. Okay, 3,900 is my principal. Oop. There we go. 1 plus is just part of the equation, always the same. They gave me a 7% interest rate. Remember to put it as the decimal value. Over, and this one was compounded semi-annually, twice a year. Remember that 2 goes in 2 places, once here on the bottom and once as part of the exponent. But they didn't know how long it took. Now what's even sneakier is they told us the amount we want to get out in a roundabout way. They said, how long will it take for this amount to double? So what is 3,900 doubled? 3,900 times 2 is 7,800. So we actually know the amount, but we don't know the time. We're working our way backwards. 7,800. Now, if you remember back in this section, I was really picky about the only thing you could clean up was this inside of the parentheses. So let's do that again. 1 plus 0.07 divided by 2, just that inside of the parentheses, is equal to 1.035. Now it's super important because it's tempting to try to multiply it by this 3,900, but remember that you cannot do that because exponents happen before multiplication. So the only thing I could clean up was this inside of the parentheses. Without knowing the time t, I can't go any further. So I'm working my way backwards. This is stuck together, this is the exponent, but this is a multiply. This is just a regular number. So I can undo regular number multiplication by dividing. So I can divide both sides by the 3,900. And hopefully it's pretty unsurprising that that gives you right back the 2 that we doubled to get the 7,800. That leaves us the 1.035 to the power of 2t. Notice I didn't really put parentheses anymore because he's all done. It's just a number. So now it looks just like these guys, doesn't it? Okay, so it's weirder numbers, but it's the same story. So I'm going to switch it into log form. So I'm going to write it as log base, the weird decimal, 1.035 of 2 equals the power, the exponent, 2t. Okay, base, the logarithm always equals the power, so these are a little bit backwards. Okay, this is just something we can plug in the calculator. So I would just type it in, log of 2, close that parenthesis, divided by log of 1.035. Don't worry, calculator can do it for you. That's equal to the 2t. So whatever crazy decimal that gives you, you're going to take that crazy decimal and divide it by 2. So let's see what that crazy decimal is. Log of 2 divided by log of 1.035. Make sure to close that parenthesis right here on the 2, and you should get 20.14 ... So if that's equal to 2t, I would just cut it in half for my final answer of 10.0744, because it's 395, so that would round up to 40. Oh, hang on, no, it would just round up right there anyways, 44. All right. Now remember that this was a word problem, and the good thing about word problems after you get past the fact that you kind of set things up is that you have context. So we were asking how long it took for our money to double, and our answer was 10 and some change, about 10 years. Does that seem like a reasonable answer? I think so. Now, if I got a negative, I'd be pretty suspicious. My money shouldn't be doubling in negative time. If I got like 8,000,000,003, I'd be kind of suspicious. I'd probably expect my money to be doubling a little bit faster than that. Probably not today because like I was talking about, interest rates are terrible. But if you had actually found a bank at 7% interest, first off, call me right away, okay? Let me know where that is. We're all gonna go put all our money there. But after that, then we would go and see how long it would take our money to double using this equation right here. All right. Next, let's see what we would do if we had compounded continuously interest. So that means every fraction of every second. This n right here gets infinitely large. Now here's the nice, quick, shortened formula for continuously compounded interest, PERT. The principal, that funny number e, which is exactly where it came from, was this equation right here, raised to the power of the interest rate times the time, PERT. So it's nice and super easy. If for some reason you forget it, you could still use this formula and just make this number here really big. Put it as like 2,000 in both of these places, and you get the same answer. But PERT is much easier. So it says same story, same bank, same interest rate. They just change their compounding. How long will it take to double our money if it's compounded continuously? Do you think it would take it longer or shorter? Is it better or worse to compound continuously? Well, remember, it was better. It kind of got less and less better, but it was still better. So I'm going to guess it's going to take less time. I expect this answer to be smaller than the 10.0744. It should be less time. Okay, so here's our formula. The final amount we want out, 7,800, equal to the amount we put in, 3,900, e, the number e, not a variable, raised to the power of interest rate times time. But again, I don't know the time. Now this one, it just saves me the step. I didn't have to do this right here. I do the same, divide by the 3,900. And again, hopefully unsurprisingly, we get a 2 because we doubled to make it the 7,800. E to the RT. Okay, that's a 7. So if I switch this to log form, that would be log base E. But log base E had a special name. Log base E was ln, natural log. So that means this could also be written as ln of 2. And that's handy because we actually have a button on our calculator for ln of 2. ln of 2, straight off of our calculator, is 0.693 blah, 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 blah. 693 blah, blah, blah. So then I'm going to take that and of course divide it by 0.07. And that's going to give me a number that is just like I expected, less than 10. Now it's not way less than 10. It's just a little bit less than 10. Because we saw that compounding more and more times eventually kind of leveled off in its goodness, but it was a little bit better, just like I expected. Okay, now what's awesome is that this works out very consistently. So every time that you're asked to double something, you would have doubled the number, and when you divide, you'd get your 2 right back out. Every time it's compounded continuously, you would have an E, which means right here it would always turn into an ln. So every time that you're asked to compound it continuously, if you wanted to find out your doubling rate, all you would do every single time is your ln of 2 and divide it by the interest rate. That's all we did. ln of 2 divided by the interest rate equals the doubling time. So that's a super cool shortcut. So making sure you watch this video gets you this super cool shortcut for doubling time. Okay, ln of 2 divided by the interest rate. Now, if you wanted to triple it, it'd just be ln of 3. If you wanted 5 times the amount you put in, it'd be ln of 5. But every time we do ln of that divided by the rate. And that worked out nicely because the compounded continuously formula was so much simpler. All right, one more. It's the last one, guys. Here we go. Suppose the population of a city is given by this equation. It's the best kind of word problem. Blah, blah, blah equation. It says where t is the number of years from now. So that means 5 years later, we put in a t of 5. So t is not the year itself. It's not 2025. T is how many years later from right now. Okay? So it says, knowing that, how large is the population right now? If they asked how large was the population 2 years later, okay, just as an extra example, then it would have gone 100,000 times e to the 0.05 times 2, and I would have figured that out. But if it's right now, well, how much time has passed if it's right now? 0. It is right now. So 100,000 times e to the 0.05 times 0. Well, anything times 0 is 0. And anything to the power of 0 is what? Not 0. It's 1. So that'd be 100,000 times 1, which is just 100,000. So it should make sense. If it's right now, the population hasn't had time to grow any, just like a principal up here. The principal hasn't grown. It's just the original right here. So if it's right now, it'd be this. If they did want it some amount of time later, we'd plug it in, figure it out. But right now, it's right now. The easiest problem in the whole thing. Seems like a really good one to put on a test. Wink, wink, hint, hint. So don't miss out on this super duper easy point problem right here. This number, boom, very little math. I really didn't even have to do this. We could have just said, oh, there it is, boom, done. All right, that finishes it up. That is the last of college algebra. So I hope you guys enjoyed these videos. Have a great day.